by, well, we can think about this as a value of a function. X squared plus 1x divided by x squared minus x equals m, and apply the Vidal's rule. So here, Vidal's rule tells you that this is the same as the motion of derivative numerator and denominator. And this is now quite obviously 1. So we take out n, B, a little bit more confusing. We have this term minus 1 to the power n times 1 to n. So this thing will make the numerator either a bit smaller than n squared or a bit larger. And you can't just apply the Vidal's rule because minus 1 to the power n is not really a value of a function minus 1 to the power x equal to n. There is no such function minus 1 to the power x. You can't compute minus 1 to the power 5.5. There is no square root of minus 1. Zero numbers. So in this case, we should do something a little bit trickier. And what works here is applying squeeze theory. So in the numerator, I add at most 1 of n. So I add at most this thing. And at least, well, the worst I can do to make it smaller is actually subtract this one. And squared minus 1n. And you see that the limit, this is just computed, the limit is 1. This, well, just think that in this calculation instead of plus 1 and we have minus, and nothing changes, the limit is still 1. So this thing that exists is equal to 1 by the squeeze theory. So what I did, I pulled out the n out of numerator and pulled out n out of denominator. So I see that both numerator and denominator behave roughly like n. So the dominant term, the one that makes this thing actually large, is this n. Two times n. So I pulled out the largest power of n, and then fix it out, and then
how did you know that you have to use squeeze instead?
So I can't talk about the function minus 1 to the power x. So to use the Vidal's rule, you have to talk about derivatives of functions. But there is no such function minus 1 to the power x. You can't compute minus 1 to the power 0 half. What does it mean? Square root of minus 1? No such thing. Even worse, it's minus 1 to the power 5. Doesn't make any sense. So to deal with this minus 1 to the power n, it's something which goes on inside, from minus 1 to 1. So I know that I will be subtracting most 1 of n and adding most 1 of n. So I can bound my complicated sequence between two sequences of the same. And both sequences actually have the same meaning. And the way I kind of know that this will work before I make the computation is the Vidal's rule. I remember that logarithm of n grows pretty slowly. I mean, logarithm of, think about logarithms basically counting the number of zeros, well, maybe like some number. So one number is some approximation, something like 3 times the number of zeros. So it grows, but it grows pretty slowly. And square grows much faster. So basically, when I look at this expression, I see n squared plus a small correction divided by basically n squared. So I know it's approximately 1. So I guess this thing that exists is equal to 1. And then I try to do it. So for C, the logic to this theorem would not work. The reason is because, well, if you try to bound this numerator between two things, well, it's n squared plus minus 1 to the power n is n squared. So this theorem doesn't work. If you try to do just the same thing, n squared plus minus 1 to the power n, n squared minus 1 to the power squared minus n. This is at most 2 times n squared minus 1 divided by n squared minus n. And at least, well, if this is actually a minus sign, we'll get minus 1 by n squared minus n. This thing tends to 0, this thing tends to 2. Well, this consideration itself doesn't tell you much. It just tells you, well, squeeze theorem doesn't apply here. But actually, for all n squared plus minus 1 to the power n, n squared minus 1 divided by n squared minus n. For all n, this is actually a minus sign, so we have f minus 1 over n squared minus n. And this thing for large n is approximately 0. But for even n, n squared plus minus 1 to the power n, n squared minus 1 plus n squared minus n is 2n squared minus 1 divided by n squared minus n. This thing tends to 0, this thing tends to 2. So you should imagine that your sequence alternates between a number close to 0 and a number close to 2. For all n is close to 0, for even n is close to 2. So of course it doesn't have any. So let's discuss D. So we already experienced the sequences. We see this term minus 1 to some power. Let's try to imagine how it's the case. Well, in this case, it's minus 1 to the power 2n. And 2n is always an even number. So it's minus 1 multiplied by itself an even number of times. It's always plus. So an is equal to actually n squared plus another n squared minus 1 divided by n squared minus n. So n squared minus 1 divided by n squared minus n equals to 2. So we think this minus 1 to the power 2n is just a confusing way to write 1. It's always 1. It's minus 1 to the even power. And finally, the last one, well, minus 1 to the power n times cosine of phi n. Okay, that's a little bit even more confusing, but think about it. So minus 1 to the power n times cosine of phi n. When n is even, cosine of phi n is 1, and minus 1 to the power n, so it's 1 times 1 is 1. If n is even, if n is both, cosine of phi n is minus 1, but so is minus 1 to the power n. Minus 1 times minus 1, which is also 1 if n is both. So this confusing term, minus 1 to n cosine of phi n, is always 1. Another confusing way to write 1. So an is once again the same thing. Now, a question about these things. So the different limits A, B, C, D, E require different totals. The first one was basically just a Gauss theorem. Second one was a little bit trickier, squeeze theorem plus the Charles theorem to compute these things. Third one required you to imagine what happens when n is in and n is odd. So this term minus 1 to the power n is squared. You know how to compute this to the lower function over the sequence. For d and e, well, the same trick. You have to imagine what happens when n is even and n is odd, except, well, it doesn't matter in these cases. The increasing terms are just 1. Okay, so, any questions? Alright, so, in the end of the last lecture, we started talking about sequences which are increasing, decreasing. We introduced the new word monotone sequence, which stands for a sequence which is either always increasing or always decreasing. And so, reminder, monotone stands for always increasing. Never changing fine. So if it starts increasing, then it continues. So this time I'll introduce a new word. AM is bounded if AM is between some numbers. Between some number n and some number m. Or all of some and m and all indices m. So I want all values of the sequence to be bounded from below by some number and from above by some number. It's really a simple concept, so let's give some examples. Something like minus 1 to the power n is bounded. Why is it bounded? Well, minus 1 to the power n is always between minus 1 and 1. Another example, 1 over n is 1. Right, this one is bounded. Well, 1 over n is always positive. That's one simple observation. Another one, n is a natural number, so it must be at least 1. So the quotient is at most 1. Another example, n squared is not bounded. Where this compound. So, the sequence n squared, sequence of squares, 1, 4, 9, 16, and so on and so on, eventually gets larger than any fixed number. You can find some square which is larger than whatever fixed number. So if you tell me that your sequence is bounded by some number m, I'll give you some number n for which n squared is even larger than this. So this thing cannot be bounded by n. It can be bounded from below, and squared is always positive for instance. But not from above. So being not bounded basically means the sequence escapes to infinity in one of the two directions. Either positive infinity or negative infinity. Or sometimes both. So another example. plus even squares or minus odd squares. So such a thing will define an even square which is larger than any number, and an odd square which is larger than any number. So this thing becomes arbitrarily large and positive, arbitrarily large and negative, and it keeps jumping from being large positive to large negative, and vice versa. But anyway, it is not bound. Okay, so what's important here with these new words is the following fact. If an is monotone, and bounded, then there's a limit. So if you imagine that your sequence is bounded, so it's between some number n and some number n, so it's always somewhere here. This is not enough to guarantee that it's bound. That there's a limit. You can imagine some sequence which keeps jumping between these two bounds. But if in addition you know that your sequence is always, say, increasing, then it's enough. Then you know it increases up to some limit. Something like this. So it approaches some number. Or if it decreases, same thing. If it decreases and stays bounded, it must approach a number. And just one of these conditions is not enough to guarantee this. You can have a sequence which is increasing, like n squared, which doesn't have a limit. Or you can have a sequence which is bounded, like minus 1 to the power n, also is bounded. If both are correct, then it has a limit.
Sorry, so what you're saying, if you want, well, if you only do one thing, right?
Yes.
So this is only have you.
No, it can be, so to do both, you have to do that.
Yeah.
Increase and decrease, so there's no limit. One is always doing the same thing. Okay, so that's the fact. Let's see an application of this fact. Surprisingly, this fact is useful for justifying existence of some limits, or even computing some limits in situations where other rules will work better. So to give an example, for these other questions about the other words, bounded, monotone, or is that bounded, monotone sequence as a limit. So let me give an example of application of this method. it's an employee about whom we don't really know much, but we don't know the starting salary. We just know that it's not larger than $100,000. We also know that in the end of the year there is a review of the salary and it increases every year by the following amount: 5% of the gap between the current salary and $100,000. And the question is, can we tell what will happen to the salary after many, many years? So basically the question is about the limit of this sequence of annual salaries. So let's write down in formulas for this problem tells you in words. First thing, let AN be the salary after 10 years. We know that the next salary is going to be the following. It's what it used to be plus some increase. And this increase is 5% of the gap between $100,000 and the current salary. So now we have a sequence which satisfies some recurrence relation. The next term can be computed from the previous one. The question is, of course, what is the limit of this sequence? Well, so here are some observations. First of all, the sequence is increasing. Why is it increasing? So, in the end of the year, you add to the salary some positive amount, 5% or whatever. You add a positive amount. So AN is increasing. Another thing, it is bounded. Why is it bounded? AN, well, it's bounded by $100,000 because you started below $100,000 and then you increase the salary every year, not enough to jump over 100,000. You don't cover the whole gap, you only cover 5%. So AN is smaller than $100,000. So, and it increases. So of course it is bounded from below by the initial salary. So this thing is bound. Yeah.
The thing was $100,000. I guess that's an exponential. That's an increase that decrease rate. Can you see that we use 100,000, so can it be equal to 100,000?
No. So what happens is, suppose that right now the salary is smaller than 100,000. What's going to happen next year? Well, it's going to increase, but the gap between the current salary and 100,000 is not going to be covered entirely, only 5%. So the next salary is still going to be extremely smaller than 100,000. But then the same logic applies over and over and over. So it always increases by some amount and never jumps over $100,000. Alright, so we have these iterations. This then tells you the sequence must have a limit. It's increasing, it never goes above some number, so it must reach some limit. Hence, AN goes to some limit, then goes to well, that's already some information, so we know that the employee will have some kind of job security, his salary will not be changing that much after many years. But that's not enough to satisfy our curiosity. We actually want to know what is this thing. So here's the trick. We take this recurrence relation and we see what happens to it in the limit. So when n is large, so let me rewrite this once again. An plus 0.05 times 100,000 minus an. When n is large, the right hand side goes always to limit plus 5% of 100,000 minus the limit. That's what happens to the right hand side. When n is large, this thing is close to this number. The left hand side, well, when n is large, all the elements of the sequence are close to the limit, to L. So in particular, the first one is also close to this limit. But these things are equal to each other. So their limits must be equal to each other. And now we have an equation which must be satisfied by this limit L. So it's easy to solve. So L is cancelled out. And we get 0 is equal to 0.05 times 100,000 times L, or L is equal to 100,000. And that's the answer. After many years, the salary of the employee, well, it's never going to become exactly 100,000 because we just observed that it's always smaller. But it's going to be closer and closer to 100,000. It will approach 100,000 and very close to 100,000. So if you think about the timeline, it starts with a salary of 0 or close to 0, like this, somewhere here is 100,000. So first year you'll get $5,000, second year you'll get an additional $4,000 and something. But eventually, the salary is going to stabilize and reach this limit of $100,000. And the funny thing here is, it doesn't really matter where he starts. Eventually, all these things converge to the same thing. Any questions about this one? Yeah.
So basically, if we know the bounds, then we basically know the limits.
Not quite. So in this case, it was the incidence that the bound was equal to the limit itself. It could be that you know that for some reason his salary is never going to reach $200,000. Somebody maybe tells you that by contract he's not allowed to get that money. And with the same conditions that every year 5% of the everything current salary is $100,000 is covered. So the limit is still going to be 100,000, but the known amount will be 200,000. So they don't have to be. The way we found this limit was by passing to a limit it is recurrence relation. Yeah.
If you really look at it, you have to show that. I don't know we just show the calculation.
So this is just, the graph is just for the convenience here, because so we discuss on what happens and we want to imagine how the salary actually goes over time. Like this, that's the only way to find the limit. So the previous considerations just tell you there is a limit, to find the limit, you take this recurrence relation and pass to the limit. write the formula. Well, you can try. It's not even that complicated, but it is more complicated to just learn this basically this way. Okay, other questions? Alright, so one sequence which is really important, but also really simple, is the so-called geometric sequence. This is just the sequence of powers of the same number. You take some number r, and you consider the sequence of r to the power n. So it goes like this: r squared, r cubed, r to the fourth, and so on. And in this case, it's quite easy to discuss when the sequence has a limit when it doesn't. So if your number r is between -1 and 1, not because it's -1, but because it's 1, or rather like this. So if it is strictly between -1 and 1, then limit of r to the power n that goes to infinity is 0. So if you take the number between -1 and 1 and keep multiplying it by itself, you're again going to get closer and closer to 0. So example, so here I choose the number -1/2 between, so here is r is -1/2. The sequence is -1/2, 1/4, -1/8, 1/16, and so on and so on. Eventually, the terms become smaller and smaller, and they converge to 0. And that is for every number to -1. If r is 1, well, then the sequence is just 1, 1, 1, 1, 1. So the limit is 1. Call this even more or less. And finally, if r is at least 1 or r is at most -1, limit of r to the power n is not existent. And that's also this. If you take a number, say, larger than 1, and keep multiplying it by itself, you'll get numbers which keep growing. So they become larger and larger and larger. Think about 2, 4, 3, and so on and so on. So, for example, larger than 2, the n is 2 to the power n, which as a group becomes larger and larger, becomes larger and larger, goes to infinity. So there is no limit. So that's one sequence. We'll devote some special attention to it, even though it's simple. It will appear once again next hour. Once again, we will discuss Taylor series. So it's important to recognize what when it has a limit and doesn't. So basically, when number from -1 to 1, it has a limit. For 1, it has a limit. But for numbers which are larger than 1, or equal to -1, it has no limit. expressions about this thing. Okay, so we discussed sequences, and actually, well, I didn't tell you when we were discussing sequences, but actually we were discussing those just because we want to discuss series later. And we'll discuss those once again only because we actually want to discuss Taylor series even later. So, let's start discussing series. These are expressions of the following type. Sum, a, from 1 all the way to infinity. So take a sum, but not the sum of finitely many terms like you are used to, but rather a sum of infinitely many terms. So in other words, it's a1 plus a2 plus a3 plus and so on. We kind of discussed one way to form an infinite sum. It was integral. This is a different kind of infinite sum. But we'll see that they are somewhat related. So, what do we even mean by sum of infinitely many terms? Does it ever make sense? Well, let's see one simple example where it obviously makes sense. So, example, sum of 3 divided by 10 to the power 8 from 1 to infinity. Let's see what it is. So when k is equal to 1, it's 3 over 10 plus k equal to 3 over 100, k equal to 3 over 1000, and keep adding a 0 to the denominator, so 0.3 plus 0.03, 0.003, and so on. So it makes sense to say that this limit, you add more and more 3's to the right. So we have 3, 3, 3, 3, infinitely many 3's. And you know that this number is actually for some familiar number. It's actually 1/3. So at least in this main way of interpreting this sum, well, it makes sense to say that this sum is actually equal to 1/3. It's a finite number, even though there are infinitely many sums. But in general, what do we actually mean when we say that some infinite sum has a finite value? What do we mean by this? Well, in general, we say some infinitely many terms in k is equal to some number when the sequence of partial sums this sequence you compute the sum of finitely many terms, the first 10 terms converges to L. So what we do here is basically for every n we compute the sum of first n terms. Then we write these sums in a list, we form a sequence, and we see whether eventually the sum becomes closer and closer to some number. If it does, we say that this number is the value of this infinite sum. So here the sequence of partial sums will be 0.3, 0.33, 0.333, and so on. And of course, it converges to this number 1/3. Or let's get another example. Sum of 1 infinity, 1 over k minus 1 over k. So this sum is, well, first of all, we just look at this expression. It's not obvious how to deal with it. So the k is equal to 1, it's 1 minus 1/2, 1/2. In k is equal to 2, it's 1/2 minus 1/3, 1 over 6. 1/2 and 6, then k from 1, k to 3, 1/3 minus 1/4, 1 over 12. So evaluating these terms, it's not quite obvious what the pattern is. So now, let's keep it like this. Let's compute partial sums. Let's compute the sum of first and terms. Let me write explicitly what the sum is. It's, when k is 1, it's 1 over 1 minus 1 over 2. When k is 2, it's 1/2 minus 1/3. When k is 3, it's 1/3 minus 1/4. You keep increasing this k until you get n. So you get 1 over n minus 1 over n plus 1. Does anyone see what the sum is actually equal to?
Yes, because I think that when I look at something that's decreasing at a slower rate, like the beginning it decreases faster, and as it slows down, the numbers gets as the key value gets larger, so I think like it's approaching 0.
Okay, so what approaches 0 is each one of the individual brackets. So as n becomes larger and larger, the bracket, the term of the series goes to 0. That's right. But what I'm talking about now is not the term alone. It's the whole sum of the first and term. Yeah.
1?
Okay, so the sum is close to 1 but not quite 1. For now I just want to find the sum itself. No, there are lots of consolations here. If you just ignore these brackets, and of course we can ignore the brackets, it's just a finite sum. We have minus 1/2 plus 1, minus 1/3 plus 1, minus 1/4 plus 1/4 here, and so on until this thing, well, not quite. You have this 1, this doesn't cancel with anything. So 1 minus 1 over n plus 1. So if we sum up the first n terms, there will also be an answer which is 1 minus 1 over n plus 1. If we sum up these remaining terms, well, the final sums approach 1, so they become closer and closer to 1 as n goes to infinity. So we say that the infinite sum from 1 to infinity of 1 over k is 1 over k plus 1. If you want to impress somebody who didn't take this course, here's another sum which is as easy to compute as the previous one, but looks much more impressive. now it's something like this: 1 divided by 1 times 2 plus 1 divided by 2 times 3 plus 1 divided by 3 times 4 plus and so on. I claim this sum is still equal to 1. In fact, I actually claim it's exactly the same sum. So I claim there is such equality. This thing is exactly the same as this one. You can just bring these things to the common denominator and write it this way. But this sum, though, there is no obvious way to compute it if you don't know this thing. So this sum is